We were talking about a couple things with initial conditions. Actually, before I get to that, let me remind you that the homework number one is due today. Most of you have already sent your papers to me, but if you haven't, please do so. Um, and homework number two, related to the particle in a box, is posted on the Google Drive now. And it's going to be due a week from today, so February 11th. Okay, so what we were discussing in the previous few classes is the particle in a one-dimensional box. Okay, and so when we're solving this problem, we want to get a solution to Schrodinger's equation. And it should also satisfy the boundary conditions, and it should also satisfy the initial conditions. Okay? And we came up with this general solution, which is a sum of separable solutions like this with coefficients Cn. And this general solution satisfies Schrodinger's equation no matter what these coefficients Cn are. And it satisfies the boundary conditions, no matter what these Cn are. Right? But that still leaves the initial conditions. So the initial conditions are what have to determine the coefficients. And so then those coefficients are going to determine what state or combination of states we might have. And that'll give us the movies, and it'll give us the expectation values, things like that. Okay, so we know that these CNs are determined by the initial conditions, okay? And then the question is, well, how are they determined by the initial conditions, right? So if we know the initial wave function, what do we need to do in order to get out the CNs? Okay. So I started to talk about that on Tuesday. So let me remind you, I've got my slides here from Tuesday. Okay, so one possibility is if you are very lucky, then the wave function in the initial condition matches one of the pure separable stationary states. Okay? And so here I had an example. Maybe it matches state number 13. Okay, in that case, we know what to do. We know that the coefficient C13 must be 1, and all the other C coefficients have to be 0. So we have this pure state, number 13, and it's going to evolve in time with this exponential factor, with the e to the minus I E13 t over h bar. Okay, so that's the situation if the initial wave function matches one of the special separable states. Okay. Now, if you are not that lucky, but you're sort of medium lucky, then maybe the initial condition is the sum of a few of the pure states. Right? So here in this example, maybe the initial condition just happens to be a sum of state number 13 and sum of state number 14. Right? So in that case, we could read off what are the coefficients of state 13 and state 14. That tells us those coefficients. All the other coefficients are 0. Okay? And in that case, we can plug those coefficients into the general solution, and we say, well, now our general time-dependent solution is the sum of state 13 with the way that state 13 evolves in time, plus state 14 with the way that state 14 evolves in time. Okay. And then this gives us the general wave function depending on time. And then we could make movies of the wave function, or we could make movies of the probability distribution, or we can calculate expectation values that depend on time. Okay, so that's the medium lucky possibility. Okay, now what if you are unlucky, right? And the wave function is just, the initial wave function is just something else, okay? So what if the initial wave function is some other function of x that's not one of these signs? Okay, so in the class on Tuesday, I tried to ad lib an example. That's not actually a very good example. I was trying to match the boundary conditions, but that one doesn't. What I meant to say for an example is, what if you have some function of x, so psi of x and 0, is a function of x that satisfies the boundary conditions. And so it's 0 here, it's 0 over here, and in between it's some other continuous function. I don't know, maybe it's a parabola that comes up and goes back down again. That's what I was trying to make up on Tuesday. So what I really meant was a function like this one, which is a parabola, parabola pointing down, and it's guaranteed to be 0 when x equals 0, and it's guaranteed to be 0 when x equals a, and in between it's something else, right? So maybe your function looks like that, or maybe your function looks like, I don't know, any weird thing, something like that, okay? That matches the boundary conditions at the two ends, but in between it does something strange. Okay, so then the question is, what do you do with that, right? So that is not a single separable solution. That is not the sum of separable solutions. So what is it, and how does it evolve in time? Okay, so if you look at a function like this, okay, you say, oh, it's not a sum of signs, right? The separable solutions. But if only we could write it as a sum of signs, then we would know what to do. If only we could write it as a sum of signs, then we could do this medium lucky case, okay? So it's not a sum of signs, but is there any way we could express it as a sum of signs? This might remind you of something that you've seen in math classes, okay? And what it might remind you of is the idea of a Fourier series. Okay, so the idea in a Fourier series is that you have some function f of x, and you express it as a sum of sines or cosines or complex exponentials. Any of those things, right? But it's the same idea, okay? And so that's what we want to do here, right? We want to take a function that's not a sum of signs, but express it as if it were a sum of signs, okay? And that is a good approximations. And in your math classes, they will teach you proofs, okay? And they will teach you proofs that if you add up enough sine terms, well, not enough. If you add up an infinite number of sine terms, then the series approaches the function that you started with. And there are mathematical definitions of what it means to approach the function, which I'm not going to go into here. Okay. Now, you might be thinking to yourselves, does that really work with any function? Doesn't it have to be like a periodic function, right? Maybe that's what you're thinking to yourself. Okay, so let me show you how what we're doing is similar to a periodic function. Okay, so first, let's suppose we have an odd periodic function with a periodicity of 2a. Okay, so you know the word odd means that f of negative x is negative f of x. Okay, so like a sine function, for example. Okay, so here I'm going to attempt to draw an odd periodic function, f of x, as a function of x, okay, with a periodicity of 2a. Okay, so here's a. No, that's not a, that's 0. 0, a, 2a, 3a. And here is negative a, negative 2a, negative 3a. Okay, so my odd function is going to look something like this. All right, that looks sort of like an odd function, doesn't it? It's not the world's greatest drawing, but you can probably tell what I'm trying to do. Okay, now it's periodic, so I have to keep repeating it, right, with a periodicity of 2a. So let me attempt to do that. That's sort of a repeat. Okay, now I'll keep trying to repeat. All right. Well, it's not the greatest drawing in my life, but it's sort of a drawing of a periodic function with periodicity of 2a. So that is, we can look over any region of 2a, okay, and that's one unit of the function, okay, and that keeps repeating, okay, every 2a. So for sure, it's periodic with a periodicity of 2a, and it is odd, right? If you reverse the sign of x, you reverse the sign of f of x. Okay, and so when you were studying periodic functions in math classes, you learned that this can be represented as a sum of sines, okay? And so it could be represented as, let's see, a sine of what, okay? Well, let's make up a sign that has the same properties, okay? So we know that sine of x is odd, and it has a periodicity of pi. Okay, so sine of pi x has a periodicity of 1. Whoops. sine of x has a periodicity of 2 pi, excuse me. Sine of x has a periodicity of 2 pi. Sine of pi x has a periodicity of 2. Sine of pi x over a has a periodicity of 2a. So that is one function that has the right periodicity. Okay? But if we want to represent an arbitrary, funny-looking function, like the one that I just drew, we need to add up this sign plus higher harmonics, that is integer multiples of pi x over a inside the argument. Okay? So we could write this then as f of x equals the sum over n equals 1 to infinity of some coefficient. For now, I'll just call it b sub n. It's related to the c's, but not exactly. Okay, b sub n times sine of n pi x over a. So this is an example of a Fourier series. Okay, it's a Fourier series with all sine terms because we have an odd function. Okay, if we had an even function, we could do something like this with cosine terms. If we had an arbitrary function that's not even and not odd, we would need both sine terms and cosine terms. Is this kind of familiar from any of your math classes? Okay. So which math classes at Kent State talk about this? Is this in like Calc 2 or where do they talk about it?
I remember we talked about this on mathematical methods in physical science class.
Okay,
Yeah.
good. Excellent. Okay, and so then, in a class like that, they would have given you proofs. Okay, and so they would have given you proofs of, how do you know that this function represents, the arbitrary thing that I drew. Okay, and it approaches the function when you include an infinite number of terms, but what does it mean mathematically to approach a function? Okay, so I trust that the Kent State Math Department would have gone over that sort of thing. Okay, so this works with a periodic function on an infinite domain. Okay, so it's an infinite domain, that is x is going from minus infinity to infinity, right? So the function is periodic and it covers infinite x. Okay, now, so here, I'll write that out. Here this is on an infinite domain. Okay, now the point that I want to emphasize is that the same thing works when you have a finite domain, okay, even if the function is not periodic. Okay, so let me make a copy of this graph with my handy lasso, and I'm going to start erasing. Okay, whoops, oops, it didn't work. Try again. Copy. Oops, I didn't mean that. Okay. paste. Okay, so this Fourier series represents the function on the infinite domain. Okay, but now suppose I start erasing. Suppose I say, I don't actually have a domain that goes all the way from minus infinity to infinity. I only have a domain that goes from negative a to a. Like that. Okay, so now here is a non-periodic odd function, okay, on the domain from negative a to a. Okay. But, you know, if the Fourier series worked for the infinite thing on the last slide, then for sure it works for this thing on this slide because it's the same function. I just did some erasing. Okay, so I could say it also works for an odd function on the finite domain minus a up to a. Okay. And now, well, if you believe that, then I can do a little bit more erasing. What if I erase this side? Okay. So now if I erase this side, then I can say, oh, well, if the function, you know, f of x is represented by that Fourier series, then it still works now, even if after I've done that erasing. Okay, so I'll say it also works for any function on a finite domain of x goes from 0 to a. So this is for any function on that domain. Okay. So that's what I want to do here. Okay, to say, suppose my initial condition is this funny thing. Okay, whatever function I drew. I want to represent it as a Fourier series here. Okay? And representing it as a Fourier series here is the same thing as representing it as a sum of the special solutions, because the special solutions are the functions just like that. Okay, so that means I could take this thing and say f of x is the sum of n equals 1 to infinity of bn. Well, this sign is square root of a over 2 times this little psi n of x, right? It's the same thing, okay? And then let's take this thing and call it Cn. So the business of determining Fourier coefficients is equivalent to the business of calculating what are the coefficients in this expansion, right? The Cn's. Right? So if I use the idea of a Fourier series, then I can take the problem of representing, I can take the problem with any arbitrary initial condition and change it to the problem where the initial condition is a sum of the special solutions, which was the medium lucky thing, okay? And then figure out what is the wave function in the future time by putting on those appropriate time-dependent exponential factors. Okay, now, if you remember your math methods class, then you know how to calculate the Fourier coefficients. If you might have forgotten that part, let me remind you. Okay, so let's do it. Okay, so suppose you are given the initial condition, which is that psi of x at time t equals 0 is some f of x. All right? So somebody tells you this thing. Perhaps it's a parabola, perhaps it's, I don't know, whatever. And you want to represent it as a sum from n equals 1 to infinity of Cn psi n of x. Okay. Here is the trick. Okay, I'll call it the Fourier trick. You multiply both sides of the equation by any one of those psi functions, okay? Let's call it psi L of x equals this square root of 2 over a sine L pi x over a, where L is any positive integer. Okay, so we get that, and in fact, you know, this psi L is a real number. So I'm going to call this psi L conjugate. You might say, why? It's a real number. Why bother to make it a conjugate? Well, that's going to be useful for things in the future. Okay, it's going to be useful for analogies in the future. For now, that star doesn't matter at all, but in the future, at some point, it'll matter. Okay, so in that case, we have that psi L star of x times f of x is equal to a sum from n equals 1 to infinity of Cn times psi L star of x times psi n of x. Okay? So that is, you see, I took this equation and I just multiplied through by the psi L star, and I put it in the middle. You could put it anywhere, but I put it in the middle. Right? And then the second part of Fourier's trick is integrate both sides over x. Okay? So we have the integral over our range of x, so from 0 to a of psi L star of x, f of x dx is equal to the integral of this sum n of x dx. Okay, so now let's do the integral on the right side of this equation. We can do that integral by putting the integral inside the sum. Okay, so the integral of a sum is the sum of the integrals. So it's the sum from m equals 1 to infinity of Cn times, whoops, not a sum, an integral. Yikes. An integral 0 to a psi L star of x psi n of x dx. Okay, and now let's remember what these psi L and psi n are. Okay, so we have sum n equals 1 to infinity Cn integral square root of 2 over a psi, sine L pi x over a. And then we have this square root of 2 over a sine n pi x over a dx. So now let's see, this is a sum from n equals 1 to infinity, Cn. Let's see, I have two factors of the square root of 2 over a. So that's just 2 over a. Okay, now we have an integral of this product of signs. Okay, this is the same thing that we talked about in the last class. Right? Remember, I argued that if L is equal to n, then this is a sine squared integrated over the full period, which means it's a half times this periodicity, A, right? Or not the periodicity, but the domain size, A. On the other hand, if L is not equal to n, then the product of signs is positive half the time and negative half the time, and it averages to 0. So that product is, the integral of that product is a over 2 delta Ln, where this delta, you remember, is the Kronecker delta, which is 1 if L equals n and 0 otherwise. Okay. So now the 2 over a and the a over 2, those things cancel. And we have a sum from n equals 1 to infinity of Cn times delta Ln. This is now a sum of an infinite number of terms. One of these terms is not 0, okay? If n equals L, then this is Cn times 1. If n is anything other than L, you get 0, okay? So only one of this infinite number of terms is non-zero, okay? So that term is Cn with n equals L, so it's Cl. So look what we have here now. We have an equation where Cl is something, right? So this is an equation which tells us what are the coefficients, right? It tells us how you can find each coefficient, okay? If you want to know C1, you take f of x times psi 1 star and integrate it. If you want to know C2, you take f of x times psi 2 star and integrate it. And so on forever, okay, until you have this whole infinite series of coefficients, okay? And with that, you've got all the C's. Once you have all the C's, you're done. Once you have all the C's, you put it back into this kind of equation that we were working with, and then you know the psi as a function of position and time. So that is the overall map of the plan, right? So let me show you a couple examples of that in Mathematica. Okay, so let me go back. I'm here. Okay, yeah, let me switch from the iPad to Mathematica, and then you can see how it all works out. Okay, so here is my Mathematica. I go to share, Mathematica, share. Got it. Okay. So here is an example of an initial condition. So this is the example of a parabola pointing down that I was talking about before. Okay, so suppose the initial condition is x times a minus x times a normalization constant. And I already normalized it for practice before I wrote this down. Okay, so here is a plot of that function, right? In the case where the parameter a is 1. Okay, so you can see it's an upside down parabola, right? It's a parabola, it starts off at 0, it goes up, it comes back down again. Okay. A plot like this looks very similar to a single sine wave, right? If I were just looking at it by eye, I might think it was a single sine wave, but it's not exactly a single sine wave, it's a parabola. So suppose this is our initial condition, okay? Let's go through the procedure now. Okay. So I have this psi, I have the complex conjugate of that psi right here. That's the same thing as psi because it's real. I can check the normalization by integrating the product of psi star times psi for x goes from 0 to a. Okay? And that is indeed equal to 1. So that's a check. I didn't make a mistake when I was normalizing it. Okay. Now, what are these C coefficients? Okay. Well, if I want to know those things, I take my initial condition here and I multiply it by any of the psi n stars. Okay, so here is one of the psi n stars. Okay, it is sine n pi x over a times this constant of the square root of 2 over a. Right? I multiply these things and then I integrate where x goes from 0 to a. And when I do the integral, I tell Mathematica a couple of facts. I tell Mathematica to assume that n is an integer and a is positive. Okay. And so here's an answer. Okay, and so you can see in this answer that the computer calculates, it involves this kind of expression of -1 plus -1 to the nth power, right? That's a combination that you might have seen in math classes. It's the way that mathematicians write, and also Mathematica software writes something that is 0 when n is even, but it's not 0 when n is odd. Okay, so when n is even, you get -1 plus +1. That's 0. Okay, but when n is odd, you get -1 plus -1, so it's -2. Okay, so this thing in parentheses is a -2 when n is odd, and it's 0 when n is even. So this is an expression for the Cn coefficients for any n integer from 1 up to infinity. It's non-zero for the odd integers, and it's 0 for the even integers. Now, I'm not really going to go up to infinity. How about if I go up to 3? Okay, so I'll make a list of the coefficients for n equals 1 to 3. Okay, so we get, here's a coefficient when n equals 1. Okay, then it's 0 when n equals 2. Then it's non-zero again when n equals 3. All right. If I write them numerically, that's this, you can see that the first coefficient is really big, right? The first coefficient is 0.999, okay? And then the second coefficient, 0. The third coefficient is really small. It's 0.037. Okay, so that goes along with what I was showing you before, that the function, if you just look at it, it looks like the first sign in our series. Okay? And so if you represent it as a sum of signs, the 0.999 tells you it's almost identical to the first sign, right? But it has a little bit of the third harmonic built into it. Okay? If I went up to n equals 5, you would have an even smaller amount of the fifth harmonic built into it. Okay. So our series, our Fourier series for the initial psi, it is a sum of the nth C coefficient times the nth time-independent solution. So, Fourier is telling us that this is a good approximation. Well, Fourier is telling us that it is an approximation to our initial function. All right. Let's check. I'm not sure I believe that. Let's check and see if it really looks like the initial function. Okay, so here are two plots. Okay, so the blue plot is the initial function, and the orange plot is the Fourier series with these two terms in it. Okay, and you can see they're just about on top of each other, right? I don't know if you can even see the blue and orange if it comes through the Zoom. Hopefully it does. Okay, so this is in fact an excellent approximation to our initial function. Good news. Okay, so that means that we've now moved from the unlucky situation to the medium lucky situation. Okay, that we have now our initial condition that is a sum of approximately 2 signs. All right, so 2 of the pure modes. So now we can see how each of them evolves in time. Okay, so each of them evolves in time with a complex exponential with a certain energy factor. So here's the energy factor, right? This is the En that we calculated. So then I can get a psi series, which is a sum of the Cn times the time-independent solution, lowercase psi n, times the corresponding exponential factor, e to the minus I energy n times time over h bar. Okay, so here is the solution. Okay, or I could write it numerically, right? I can tell Mathematica to take all these square roots and make them numerical things, okay? So here's a numerical series. And this solution would be exact if we went up to an infinite number of terms, okay? It is approximate because we have truncated the series, right? That we don't really have an infinite number of terms. We only have 2 terms. That makes a little bit of an approximation, but it's, in this particular case, it's actually an excellent approximation. Okay, so now let's do all of our usual steps. Okay, so we've got the psi series. We can take the complex conjugate of that, okay, which just means taking the negative I to positive I in the complex exponentials. Then we can multiply it out to get the probability density. Okay. You can see that the probability density has some time dependence because it's not exactly a pure state, okay? It's approximately a pure state, but not exactly. And so there's a little bit of time dependence. Let's make a movie of the probability density. Here it is, come on. Okay, so you can see the movie's changing a little bit, but it's not changing very much, okay? That's because our initial condition here was really close to being a single stationary state. You know, it was 0.999 of an initial stationary state plus a tiny little bit of another state, okay? And so the probability density is almost constant. It's just varying a little bit because of the small amount of the state number 3. And we can get expectation values. Okay. When we calculate our expectation values, we should be alert to the fact that our normalization is close to 1, but it's not exactly 1. It's not exactly 1 because we don't have an infinite number of terms. We truncated the series. Okay? So we do need to be careful to divide by that normalization factor that is close to 1. Okay, and when we do that, we can see that the average x comes out to be a over 2. It's right in the middle. That's what we would guess. The average p comes out to be 0 because the average x is not changing. We can get out the average energy by doing this integral sandwich with the Hamiltonian in the middle. We can get out the average of the energy squared by doing the integral sandwich with two Hamiltonians in the middle. And so we can see what is the uncertainty in the energy. Okay? And the uncertainty in the energy is not zero because it's not exactly a pure state. It has a little bit of state number 3 mixed in with mostly state number 1. Okay. So that is an example where the initial state was pretty close to one of the single stationary states, but not exactly, okay? Let me show you another example where the initial state is not so close to one of the pure states. Okay. So, where's my example 2? Okay. Example 2, all right? So here, I made up a function, okay? So x to the 8th times a minus x, okay? So that's this lopsided function like this, okay? With way more of the wave function on the right side and very little on the left side. Okay? What would we do if we have this for our initial state? Okay. Well, we first, of course, check to see that it's normalized, which we always do, okay? And in fact, yes, the normalization is 1 because I already did it in advance, okay? So I didn't mess it up, good. Now let's find the CN coefficients, okay? So we take this initial state multiplied by psi n star integrated for x goes from 0 to a. Again, with the assumptions that n is an integer and a is positive. Okay, so it's a messy integral, but Mathematica can do the integral. All right, so there's an answer for the integral for every possible value of the integer n, okay? So let's try it. Let's go up to n equals 3, for example. All right. So I'll make a table of all of those results up to n equals 3. And then if I put those into the series, I could say my initial Fourier series is going to be this kind of thing, okay? So something times solution 1 plus something times solution 2 plus something times solution 3. Let's check, is this a good approximation to the initial function? Make a plot. Oh, that's kind of disappointing, isn't it? Right? It's not really a very good approximation, okay? So the initial function is blue, our approximation is orange, not so good, all right? It's not so good because, mathematically, it's guaranteed to be good if we take an infinite number of terms. But I only took 3 terms. 3 is not enough, okay? What if I did more terms? What if I did, say, 8 terms? Okay. So here's a list of the first 8 terms, okay? If you look at the numbers, you can see the numbers are getting smaller, okay? So the numbers are all pretty big for the first 3, 4, 5 terms. Eventually, they're starting to get smaller, okay? So here is a Fourier series going up to 8 terms. Is that a good approximation? Well, yeah, maybe that's good enough. Right? I mean, if I wanted better, I could do more terms. It's just, more work for the computer. It takes a lot more time. All right, so I'll go with 8 terms. Then I could take the complex conjugate. I could check and see, is this normalized. Okay, so I'll take the complex conjugate times the function, multiply them, integrate over x equals 0 to a. I get 0.99. It's close to 1, but again, you got to watch out. It's not exactly 1. All right. So how about the time dependence? Okay, so the initial state, that's where it started at time t equals 0. But what about in the future? All right, well, the future wave function is this sum of the c coefficient times the time independent psi n solution times the time-dependent exponential factor. So that makes a wave function, which is this sum of 8 messy-looking terms. The complex conjugate is a sum of 8 terms. Okay. The probability density is the product of 8 terms times the 8 other terms. I'm sure that I don't have to do this by hand. Okay. Then, what does the probability density look like in time? Okay, let's do it. Okay, so here's the movie. Okay, it starts off, you can see, with this hump over on the right side. That was the initial condition that I put in. As I go forwards in time, it gets kind of spread out. It gets kind of messy all over the place. Here, I'm going forward slowly, manually. It rearranges itself. It does some interesting things. If I'm careful and I get to just the right time, at just the right time, it actually makes a big hump over on the left side. And if I could tune it just right, I could actually see, yeah, the hump on the left is exactly symmetrical with the one on the right. Right? And then if I keep going forward in time, it does all this messy stuff, it moves around, but eventually it gets back to a hump on the right. Right? So it's complicated time dependence. Right? And then what? You know, I could calculate averages also. Okay, so let's see, can I calculate an average X? Well, sure, I just need to, well, get the normalization integral and then integrate this product of, you know, psi star times X times psi. This actually takes the computer a little time, but I did it in advance. So here's how the plot's going to come out. Okay, so you can see the plot for the average X, right? It started over here on the right side, and then it had all this messy stuff in between, and then it made a hump over on the left side. And then it has all this messy stuff, and then it makes a hump back over on the right side again. So this is a range of behavior that you can find if you have a complicated initial condition. Okay, so an initial condition that is not approximately 1 or 2 of your special pure states, but instead is this whole messy combination, which can be approximated as a whole bunch of these pure states added together. So that is the basic strategy here, okay? So the basic strategy is, right, we want to solve Schrodinger's equation with the boundary conditions in a way that goes with the particular potential energy function, okay? When we do that, we find all the special separable solutions, and the corresponding energies. And then if we have an initial condition, we have to express the initial condition as a sum, a linear combination of these special separable solutions. And then we can put all the pieces together to get the wave function as a function of position and time. Then once we have the wave function as a function of position and time, we can get the probability density and make movies. And we can calculate expectation values, right? So that's the sequence of steps in quantum mechanics, right? So that sequence of steps, is the quantum mechanical version of like what you did in classical mechanics when you solve an equation of motion with certain initial conditions, okay? So here we have the quantum version, which is analogous in some ways, but it has a lot of steps in it, right? But you didn't sign up for the easy version of quantum mechanics course, right? So this is what you get. Okay. Now, at this point, okay, this is where some smart student asks me, do we really have to do all this stuff, right? This is all kind of old-fashioned, solving a partial differential equation in this way. Is it still necessary now in the year 2021, right? Because can't we just tell a computer, here's a partial differential equation, go solve it for me and tell me the answer, okay? So, in case any of you are wondering that, let's try an example of just making a computer solve the partial differential equation. Okay, so I will show you, this is not part of the normal curriculum for this class, but let's just see for comparison for this stuff that we're doing. Is it really worth it? Or could we just do a numerical solution? Okay, so let me share my numerical solution code here. Okay, so let's do a numerical solution of the partial differential equation with the same example initial conditions as I was just showing you. Okay, so here is the initial condition of example 1. Okay, so you remember in example 1, we had the upside down parabola that looks like this. Okay, and now I want to do a solution of Schrodinger's equation. So here is Schrodinger's equation, okay? This is the Mathematica notation for Schrodinger's equation, okay? So here on the left side, you see I h bar times the derivative with respect to time of psi of x and t. Okay? And on the right side, you see negative h bar squared over 2m times the second derivative with respect to x of psi of x and t. All right. Now, numerical solution needs numbers, right? I mean, you can't solve it with variables like m and h bar, okay? So I'll put in that m is 1, the mass is 1, and h bar is 1. Okay? So this is the Mathematica notation for that, okay? So this superscript 0, 1, it means the first derivative with respect to the second variable, which is time, okay? And here the superscript 2, 0 means the second derivative with respect to the first variable, which is x. Okay, so that is the equation that we want to solve. Okay, so here is the command for solving Schrodinger's equation, okay, numerically. Okay, so the pieces of this command, I give Mathematica a list of things that I want to solve inside of the curly brackets. Okay, so I want to solve the differential equation. Okay, I want to solve a boundary condition that psi, when x equals 0, that's equal to 0 for all time. Right? Then here's another boundary condition that when x equals 1, that is a, and time is anything, that the wave function is 0. Okay, that's my second boundary condition. And then here is my initial condition, that psi of x and time equals 0 has to equal the psi initial, the thing that I defined up here. Okay, so I want to solve all the things inside these curly brackets. And then I tell Mathematica the thing that I'm solving for is the psi function. And I want to solve it on the domain of x goes from 0 to 1 and time goes from 0 to 1. And then this extra timing thing on the outside, that's just saying I want Mathematica to keep track of how much time it takes for the computer to solve it. Okay, so here it goes. Come on, can you do it? Let's find out. Yes, okay, it did. Okay, so here, this tells us it took 10 seconds. It took me 3 lectures to do it, okay? It took the computer 10 seconds to do it. And the solution, here's the format for the solution. Mathematica calls it an interpolating function, okay? Then I'll define that the probability density is, well, it's the real part squared plus the imaginary part squared. Oops, come on. It's the real part squared plus the imaginary part squared. That means it's psi star times psi, okay? And here's a movie of the solution. You know, this actually does look kind of like the solution that I came up with, you know, in example 1 previously, right? Because this is, you know, close to our stationary state number 1 with a little bit of stationary state number 3 mixed in. And so it goes up and down a little bit. So actually, yeah, this does kind of work. You know, it all comes out consistent. Okay, it works for example 1. What else? Well, I'll skip this other thing. How about example number 2? Okay, so here's example number 2. Let's see. So for example number 2, there's the psi, here's the psi star, here's the normalization, here's a plot of it. This is all just like before, right? And now here is Schrodinger's equation that we want to solve numerically, okay? So I'm solving the same differential equation with the same 2 boundary conditions, but a different initial condition. Okay. And I'm going to solve it for x goes from 0 to 1, and now actually for time goes from 0 to 4 over pi, which is the periodicity. Okay, so let's run it. All right. When I ran this before for practice, it took 2 minutes about. So now actually my computer is also running Zoom, so it may take a little bit longer. This is where I have to keep talking and fill up the dead air. Okay, so while it's running, let's talk about pros and cons, right? Like, was it worth it for me to do 3 lectures about the old-fashioned way of solving things? Well, you know, it depends what you want, right? If you just want the solution for one set of parameters and then you're done, maybe you just want to do it numerically, right? But on the other hand, you do get some extra insight from doing the old-fashioned kind of solution, right? So the old-fashioned kind of solution tells us that there are these special states, right? Which are the sine waves, right? The sine of pi x over a and 2 pi x over a and 3 pi x over a, et cetera, right? And if we didn't do the old-fashioned solution, we wouldn't know that, right? We would just say, depending on what initial conditions we put in, sometimes we get something that's stationary, sometimes we don't. How come? I don't know. It's just how it comes out from the computer, right? So we do get a certain amount of extra perspective from knowing that there exist these special states with simple time dependence, and knowing that the general solution is a combination of those states. Okay, so here's the solution. It took 161 seconds, so it was slower than before, presumably because my computer's running Zoom. Okay, and so what does it look like? Okay. So let's see. Here is going to be the movie. I will do it forward manually. Well, so you can see it starts off with a peak on one side, and it comes around and makes something kind of messy. And then if we hit the time just right, it should make a peak on the left. There it goes. There's the peak on the left, okay? That was just like what we found before, okay? And then if we go forwards in time, it makes kind of messy things. It makes the double peak again. And if we get to just the right time, it'll make a peak on the right, okay? The peak on the right, well, it looks messier than it was before. This is part of doing numerical mathematics, right? With numerical mathematics, you can't expect to get things that are exact the way that you get when you're working with symbolic calculations. And then, well, we can get averages of stuff also. So here's the average position calculated numerically when I did it before. And it's kind of similar to the plot that I showed you from the Fourier series. Okay. So, in this numerical method, I mean, it really exists and it does get faster. And so this is one important style of working. And a lot of people do solve differential equations numerically for a living in physics research and in meteorology, in all kinds of scientific research. So it's a good skill to have. It's not a skill that I'm particularly teaching in this class, but it's a good skill to have. This class is a very traditional quantum mechanics class, okay? And it concentrates on the traditional method, which is solving the time-independent Schrodinger equation to get these special time-independent states and finding what are the energies of those things. And then to say, well, any arbitrary state is a linear combination of those things. And we can figure out what linear combination, right? And figure out the energies and the time dependence. All right, so that wraps up what I wanted to say about the particle in a one-dimensional box, okay? And so the new homework that is just posted is 3 problems related to the particle in a one-dimensional box, okay? So 2 from the textbook and a 3rd problem that I made up myself. So please get started with doing those things. And so, as of now, you have enough background information to do those things. Beginning on Monday, I will start with a different potential energy, right? So a different physical problem. And we'll see how to apply this concept of solving Schrodinger's equation to that problem. Okay, so have a good weekend, you guys, except for the homework that I just gave you, and I'll see you all on Monday. All right, thanks.